Well, hello and welcome to this very first Mid-Kent Astronomical Society virtual club meeting. It seems to have been absolutely ages since we were all able to meet up at Bredhurst Village Hall for a club meeting with a presentation, teas and coffees, a chat, and some observing in the field afterwards. But I hope that you will have all been able to take advantage of these wonderfully clear skies that we've had recently to do some observing from your own back gardens. We hope to be able to resume Bredhurst meetings as soon as it's safe to do so in the not too distant future. However, tonight we are very lucky to have Dr. Julian Onions from Nottingham University to give us a talk on galaxy evolution 1 gigayear at a time. Following his presentation, Julian will be available to take your questions on a Zoom meeting. So hopefully I'll see you all at that Zoom meeting. I'm sorry, Julian, we've not been able to arrange a virtual cake to be sent, but hopefully we'll be able to see you personally at Bredhurst in the not too distant future. So over to you, Julian.
Well, hello everybody. I hope this is coming through okay. Maybe somebody could say something in the chat if you can hear me okay. Thank you very much for inviting me to give this talk, and there's already mooted a possibility that I could come and visit you next year to give a different talk. But maybe you'd want to see how this one goes first and see if it's worth me coming along, whether it's any good, basically. So tonight I'm going to talk about galaxies, 1 gigayear at a time. That's a phrase that we use in galaxy evolution, because nothing very interesting happens to a galaxy in less than a gigayear, which is 1 billion years. So on the scale of about a half to 1 billion years, something interesting may happen in a galaxy, but otherwise they're fairly passive and slow moving things. So tonight's talk is all about galaxies, and it's going to start off fairly gently, and then towards the end I'll talk to you about a few of the interesting problems still to be solved in this field. However, before we start, I think I'd better just make sure that you're all on the same page, and that you've not all come here hoping for chocolate or indeed cake, which as was mentioned, but there we go. Oh, great. I'm just checking everybody can hear and see me. Or we're talking about new mobile phones, the latest Galaxy model, which is getting ever bigger, it seems. So neither of those. And we're also not talking about things that are far, far away. Well, we are talking about things that are far, far away and a long time ago, because that's what's happening in galaxy evolution. But it's not really the fictional universe of Star Wars, although obviously that does take place in a galaxy far, far away. So what we are talking about is these sorts of things. These are lovely galaxy images, mostly from the Hubble Space Telescope, and we have a fantastic view of galaxies there, all different shapes and sizes, and I'm going to talk you through the classification of galaxies and a few other facts and figures about them that I hope you'll find interesting, and if not, you can just look at the interesting pictures and go with that. So without further ado, we should perhaps move on. I have to say that just some of my credentials, or our departmental credentials at Nottingham University in the astronomy department, all we study is galaxies. So we are entirely devoted to galaxies. All the astronomers there and all the PhD students and postdoctoral researchers all work on galaxies in one form or another. Most of them, unfortunately, don't work on anything nearly as beautiful as these galaxies you can see here, we all work on very distant galaxies that are just a few pixels across in practice. So we don't get to stare at images like these all day, unfortunately. And just to sort of put it in context, this is an image taken by the Hubble Space Telescope over 11 days, although it didn't sit there for 11 days. It took it over a few months and stacked the data. But 11 days staring into this very dark place in the sky to produce something called the Hubble Ultra Deep Field. And here is the result. And you can see practically everything in that picture. There's a couple of stars, but nearly everything else is a galaxy. And some of them are right on the edge of the visible universe. So it's kind of galaxies all the way down. Galaxies are probably the most numerous large objects certainly in the universe. This is a joke that works a lot better in person, but maybe you'll still get it, and it just work to see if everybody's still awake. So before we jump in, I thought I'd say something a little bit about distances. I'll have a quick swig of a cup of tea. So this is the sort of most smallest distance we use in astronomy, called the astronomical unit, and it's the distance between the Earth and the Sun, which is not actually a fixed distance, because as you probably know, the Earth goes around in an ellipse, but we've sort of nailed it at a specific distance. And it doesn't really matter. It's such a big number anyway that a few kilometers either side doesn't really make any difference. So that's one astronomical unit, and we almost never use that in galaxies when we're considering them. It's far too small for anything that we do within galaxies. Occasionally we might talk about it in terms of supermassive black hole sizes or something like that, but really it's far too small to consider for galaxies. The next one up is the light year, or the parsec, and in astronomy we typically seem to use parsecs. I don't know really why, but we seem to have fixated on them. But yeah, roughly sort of 3 parsecs to a light year is the sort of going rate. But so the nearest star is 4 light years away, or around about a parsec. So if you take it as a parsec is about the distance between 2 stars, then you won't go far wrong. So that's sort of the scale. And we don't also use parsecs very often in galaxies. We tend to go for kiloparsecs and megaparsecs, and I'll explain those in a minute, or at least give you a feel for them. But first, let's talk about what is a galaxy. So a galaxy is a really large collection of stars, and it's also a factory, at least in its early days, for turning gas, mostly hydrogen and helium, into stars and getting them to burn and glow in visible light and all sorts of other lights. So, for instance, the Milky Way, there's about 400 billion stars in the Milky Way. So there's quite a lot of stars floating around in the galaxy. Milky Way is about somewhere in the middle. So there are galaxies bigger than the Milky Way. There are a lot of galaxies smaller than the Milky Way too. But Milky Way is pretty average size. And this is what we think the Milky Way looks like, although it's really hard to work out what something you're living in the middle of looks like from the outside. Obviously, we can't go outside the Milky Way, so we have to infer it from positions of stars and other things. And that yellow circle is where the sun is. And also within that circle is pretty much all the visible night sky stars. So nearly all the stars you can see with your naked eye are somewhere in that yellow circle. So we get a very sort of distorted view of the galaxy. We can only see a small part of it. Now going back to size, a typical galaxy is maybe 100,000 light years across, or 30 kiloparsecs. So that's kind of the units we use. And we're somewhere out, about halfway out. We're probably about 8 kiloparsecs from the center of the galaxy, and there's a fair bit beyond that. And we're not in even a very interesting part of the galaxy. We're off a spur of a spiral arm of something. So we're just sort of somewhere in the backwaters. But for a long time, and we've seen lots of other these fuzzy things in the night sky that we didn't really understand. And for the longest time, we weren't really sure whether the galaxy, the Milky Way, was all there was to it. Was the entire universe just the Milky Way? And these fuzzy things in it, which you can see here, the Perseus cluster, a grouping of lots of galaxies, all those fuzzy things are galaxies. Were they just part of the Milky Way? Because you can see scattered in there, we've got a lot of stars. So, and we find quite a lot of fuzzy things within the Milky Way that we know now are within the Milky Way. So there was a big debate for many years, certainly in the 1920s and 30s, about, is the Milky Way everything there is, or is there more to the universe than we can see here? And here's another cluster of galaxies. You can see also lots of stars scattered in them, the Fornax galaxy cluster. And this problem arises because it's really, really difficult to measure distances in astronomy. Things are so far away. I've said it's 4 light years to the very nearest star. So, light takes 4 years to come from that star. And it's incredibly hard to measure the sort of distance between us and that star, even for the really near ones. So by the time you get to the furthest stars that we can see in the Milky Way, it's a real struggle, or it certainly has been. And so if you want to then go on and measure the distance to these fuzzy objects, that's they were clearly not right next door to us. They must be quite a long way away, but how far away is far? And this problem was solved by Edwin Hubble, who, seen here, knew how to take a very good photograph using the Mount Wilson 100-inch telescope. So he had a good instrument at his disposal, and he managed to work out the distance to the nearest galaxy, the Andromeda galaxy, to a reasonable precision. And although it was off by about a factor of 4 or so when he measured it, it didn't really matter. It was so far away, so far beyond the furthest stars we could measure, that it was clear a separate universe, and he could see separate stars in them. So that really sort of fixed it. It ended the debate that had been going on in the 1920s about were we an island all on our own and nothing else was out there, or were there collections of these things? So that was great. We knew there were other galaxies. What do you do when you've got this sort of new breakthrough in science and you found something entirely new, or you've confirmed something is new? What do you go about doing? Well, this is a common thing that we do in pretty much all sciences, not just galaxies. So this is called grandly making sense of galaxy morphology, or can we classify them into some useful collections that perhaps will help guide us in the science later. And famously, Ernest Rutherford, who didn't work on galaxies as far as I know, said all science is either physics or stamp collecting. A sentiment I agree with, being a physicist. And I think what people have taken that to mean is that either you know what you're doing, in which case it's physics, or you don't know what you're doing really, and you just start stamp collecting. So you start grouping together things that look and seem to have similar properties, and you sort of make collections of them, and then you try and see what the commonalities between them are and see if there's any way you can connect them. Now this works really well in sort of the 1800s and so on, when they were doing it with animals. So they grouped together birds, insects, fishes and so on. These all had common attributes. Fishes all swam in the sea pretty much. Insects all had 6 legs, birds flew in the air. So we had a natural grouping, but then there were things that sort of didn't quite fit into one thing or another, and this eventually led to the theory of evolution, as we found common attributes between things. So can you do the same thing for galaxies? This is a good question. So here's a big collection of galaxies. Can we see any sort of common features between them? Well, Hubble clearly did, and he came up with the scheme that we still use today, and this is his classification. And I'm going to take you briefly through this. You've probably come across it before. I'm sure quite a few of you know it, but let's just make sure we're all on the same page. So he had this grouping here, and this is how he divided things up. So let me see if I can draw on here. Yeah. So down here we have a group of galaxies here, and these are all called spiral galaxies because they have a sort of spiral shape. They look very much like water disappearing down a plug hole. Over in this middle group we have what are called elliptical galaxies because they are, as we'll see, sort of more three-dimensional, more like footballs or rugby balls. There's a small group over here called lenticular galaxies, or S0 galaxies, and I'll come back to describe those because they're much easier to describe once I've sort of outlined features of the others. And like any good scientist, you always have a small bucket over here which you can put anything that doesn't fit into. So this is what he called irregular galaxies, and this is where galaxies that don't fit into any of the other three categories go, by and large. And he summed this up with a nice diagram here, which has been reproduced many times in many ways, called the tuning fork diagram, because you can see there perhaps it looks a little like a tuning fork, and this is where things sit on it. It's not a particularly good classification scheme because it was invented a long time before we really understood what was going on in galaxies. But we're not going to change history now, and this is what everybody learns. And there are new ways of classifying galaxy, but everybody goes back to this. So over here we have the elliptical galaxies all over here, going from E0 to E7. So E0 is an almost perfectly spherical football-like shaped galaxy, and E7 is a very stretched out one. So the number after the E says just how stretched out it is, whether it's perfectly circular, spherical, or whether it's more like a rugby ball. Then over here we have two branches of spirals, those going up here. These don't have bars across the middle, so they are SA, SB, and SC. And the letter after it says how tightly wound they are. So an SA is very tightly wound and an SC is quite loose. And then we have the same things down here, SBA, SBB and SBC. And the big B means that it has a bar across it. So you can sort of see a bar across here and a bar across here. It's a little more difficult to see it across this one. And again, they have the final letter again says how tightly wound there are. There are ones now off to this side over here, so there's an SD. I don't think there's an SBD, so an SD is a very diffuse galaxy. And then there's also the irregulars, which would be somewhere down here. And there's the other type I've talked about, the S0, sort of somewhere in the middle of it. So that's the galaxy classification scheme. And by the end of the next few slides, you'll all be pretty good experts at classifying galaxies, I should think. So let's take a look at a few galaxies. And we'll start with the nearest one, which is also behind me on the wall here, which is Andromeda. The furthest thing you can see with the naked eye, with a couple of caveats. You need to be in a really dark area to see this, and you need to have good eyesight. I don't really think I've ever seen it naked eye. I've seen it in binoculars, I've seen it in telescopes, but never quite convinced I've seen it naked eye. And part of the reason is, if any of you have seen it, I'm sure quite a few of you have seen it, that it doesn't really look like this to the naked eye. It is quite a big object. I mean, it's compared to the full moon, it is actually bigger than the full moon in its full extent. But when you look at it with the naked eye, this is kind of what it looks like. You only really see the core of the galaxy. You don't see those big spiral arms. You need a long exposure and a good telescope, good CCD or something like that to capture all the detail of it. So that's our nearest neighbour. That's the one that Edwin Hubble used to work out the distance to nearest star, nearest galaxy, and prove it was a long, long way away. So here's another one. This is a nice edge-on spiral galaxy. You can perhaps just see some of the spiral structure there. And this is the Sombrero galaxy. Supposedly looks a little like a Mexican hat. But you can see one feature of the spiral galaxy here, that it is really quite thin. You can see it's quite thin in its one dimension compared to how wide it is. So that's quite a feature of a spiral galaxy. And you can also see quite a lot of dust in it. So the dust is all this stuff sort of around here, this blackish stuff, which is the consistency of smoke. So it's fine particles of carbon and other silicates and things like that that absorb light and therefore appear dark. Here we have another one. This is NGC 1300 from the New Galactic Catalogue, which isn't that new actually. The New Galactic Catalogue was produced in about 1890, so it's a rather obscure version of the word new. But you can see here it's clearly a barred spiral. You can see the sweeping spiral arms out here going round, and the big bar across the centre with the central core here. Another feature that is quite evident in this one is the colours. So you can see the spiral arms are very, very, very blue in colour, and the centre is much sort of redder colour than the spiral arms. And this is something we're going to come back to very shortly, because it gives us our first clue about the science of what's going on in this galaxy. So another way of thinking of a spiral galaxy is it's a fried egg. This is a pretty good description of it. In fact, it's two fried eggs back to back. So we have the big bulgy bit in the centre, which is the yolk, and the spiral disc, which is the white of that's all spread out. And as far as dimensions go, it has very similar dimensions to a compact disc or a DVD. So if you think of how thick a DVD is compared to its width, that is very similar to a spiral galaxy. It gives you a feel for sort of how thin the structure of stars is compared to the width. So that perhaps helps give you some scale for that. And this is what we generally talk about in terms of naming bits of them. So the bulge is the bit in the middle. Not all galaxies have a bulge, but most do. Then you have the disk, which is where we live, which is this thin CD bit. Then there's a halo, which surrounds the galaxy. It's sort of a spherical thing and contains globular clusters, a few stars and a few other things, but it's much less populated than the disk or the bulge. The disk and the bulge is really where all the stars, the majority of the stars and the majority of the mass of the galaxy is sitting. Then all this is embedded within something much bigger called a dark matter halo. And we can't see this at all. We can't detect dark matter in any way other than by its effect on gravity. So we deduce it's there, and there's quite a lot of evidence that it is there. And in fact, I have a whole hour's talk on that, which I'm quite willing to give at some stage if you invite me back. But that governs the dark matter halo, and it's about, as a rule of thumb, it's about 10 times the size of the galaxy. So the dark matter part of the galaxy is about 10 times the width of the visible part. So you can see it's quite extensive. If only we could see it with any mechanism. So going back to galaxies, here's a nice view of M81. I think this one's taken in a multitude of wave bands, so you can see quite a lot there picked out. You can see the core of it, you can see the spiral arms going around and stretching out to the edge. M81 being a nice nearby galaxy. This is also something that works better live, but there we go. A spiral galaxy of galaxy chocolates. And here we have another one. This one is also taken with some X-rays, but it does again highlight the sort of bluish colour outside. So we have an X-ray overlaid over the visible and the red centre of the galaxy. So this, as I said, is going to give us some clues about what's going on in the galaxy. Now, to understand this, in case you're not up in stellar evolution topic, I'm just going to have a quick side step into stellar evolution, which means fancy way of saying what happens to stars in their old age. So firstly, if we look at the sun, so this is our sun, a sort of yellowish, whitish star. It's a little bigger than most stars, but only by a tiny bit. Most stars are just a little smaller than the sun, but it's certainly no monster. And it's fairly hot at 6,000 degrees on its surface, approximately. And we weigh things in astronomy in solar masses because it's much easier than writing down all those zeros if you go for kilograms. So this is the sun. Say it's a very yellowy white star, gives off most of its light in the visible spectrum, and that's probably no accident. We've evolved our eyes to match what the sun gives out. So that's the sort of colour it gives off. And the sun is a star of the sun's size and mass will last for about 10 billion years, 10 gigayears. So we're about halfway through that. The sun's been going for about 5 gigayears, so it's got about another 5 gigayears or so left in its tank. If we look at other stars, we've got red dwarfs, which are somewhere around half the mass of the sun, so about half the size, and a lot cooler. So 3,500 degrees is typical for red dwarf, half the solar mass. And because they're cooler, it's very much like if you've ever seen metal heat up in a blacksmith forge. It starts off black, but as it gets hotter, it starts to glow a sort of dull red. And then as it gets really, really hot, it starts to go up into the yellow. So these red dwarfs are not got quite as hot as the sun, so they're giving off quite a lot of light, mostly in the red part of the spectrum. So they look very red. So the sun looks quite white. And then we go to the really massive stars, things like Rigel, which are blue giants. And these are very, very hot, 30,000 degrees, and much bigger, 30 solar masses. So you could fit 30 times the mass of the sun into something like this. Rigel isn't quite that big, but I'm just picking one at random. So these are so hot, if you go back to the blacksmith and heating up this bit of iron, it would start off red, then glow white. If he could keep heating it up and it didn't dissolve, well, not dissolve, just melt into a puddle, it would eventually give off so much light in the in the very short wavelength, the blue part of the spectrum, that it would appear mostly blue. I mean, it's still giving out red and yellow light, but most of it is now coming out in the blue part of the spectrum. So these stars look very blue, and because they're very big, they're very luminous, they give off a lot of light compared to the sun. But because they are very luminous, they also burn through their fuel very, very quickly. So whereas I said the sun lasts about 10 gigayears, and a red dwarf could last up to 100 gigayears, so very, very long-lived. A blue giant, we talk now in millions of years rather than gigayears. So something like Rigel, maybe only 15 million years to be born, live and die. So, and just to put that in perspective, here's a little graph just to show how big the difference is. So you can see red dwarfs have a huge, huge life. And the age of the universe, if I put that on here, is about here. So it's not very straight, is it? But that's about how old the universe is. So you can see that no red dwarf that's ever been born has ever died yet, and has got plenty of life left in it. Stars of the sun's mass, some of them have been and gone. Our sun obviously wasn't born right at the beginning of the universe, so it's still got a little way to go. But things that are blue giants, we can get many, many lifetimes of blue giants in one lifetime of the sun. So what does that mean for a galaxy? Well, if we go back to one of these, and I said you can see the blue structure is all out here in the outskirts of the galaxy. The blue is given by these very bright stars, these very big giant stars with huge outputs in luminosity. So although there aren't very many of them, because you don't get many big stars, most stars are, as I said, around the size of the sun or smaller, but those that do form into these huge things, they give up a lot of light, so they dominate these spiral arms. But I've said they only last a few million years, and this galaxy must be billions of years old. So what does that tell us? Well, it tells us that we must be making new stars all the time in those outer spiral arms. So these are basically star factories. They're converting gas into new stars. They're making lots of suns and lots of red dwarfs, but they're also making some stars a bit like Rigel, these big blue giants, and they are sort of dominating this part of it. So that's why we see them blue. We see all this blue stuff coming out. And galaxies like our own Milky Way, they make on average about one new star every year. Maybe two or three, somewhere around that value. Of course, it takes a few million years to actually make a star, so they don't just pop into existence, but there's a continual sort of conveyor belt of gas turning into stars and forming these things, and we get these blue giants. So we see these as very bright blue areas. On the other hand, in the middle, we're not seeing any blue, or at least not very much. So there aren't any big blue stars being born in there. And in fact, there isn't very much happening in terms of star turnover in the centre. There will be a few stars dying, but there will also be a lot of these red dwarfs just hanging around for their lifetime. And that's what's sort of giving off the red colour there. So that immediately tells us part of the story of the galaxy from just that. And we can see this also illustrated here in a whirlpool galaxy, which is a very nice nearby galaxy, M51, that very favourite of astrophotographers. It's also being harassed by this smaller galaxy over here, which is sort of starting to attack these stars over there. But you can again see the blue out in the spiral arms and the red towards the centre. The other thing that we know about spiral galaxies is that they are very ordered. All the stars are basically going round together like this. They're all going around the centre in this plane of the either the fried egg or the DVD disc, whichever you like. So they're all going around together, and for the Milky Way, it takes about 250 million years to go around once in an orbit. And it's interesting to think what life on Earth was like last time we were in this place. 250 million years ago, I think life was sort of starting to come out of the oceans onto the land. It was that sort of era. You could speculate about what's going to be happening 250 million years into the future when we're next back at this spot. Will lockdown have finished by then? Will Brexit have been sorted? Who knows? Yeah, things yet to be seen. Now, if we go into the other major type of galaxy, so the two main types of galaxy are the spirals and then these type, the ellipticals. They sort of dominate the types of galaxy. If we look at a typical elliptical here, NGC 4150, you can see it's much more boring. There really isn't very much interesting happening. There's a little bit of dust happening in towards the centre. You can sort of see these little dust trails here. We can see a bright centre, and then it sort of gets dimmer and dimmer and dimmer as it comes out, and you're never quite sure really where the galaxy finishes. So that's what a elliptical galaxy looks like. Very fuzzy blob, but not really very much structure to it. And the other key thing about these is they are very three-dimensional, so they are much more like footballs or rugby balls. They have a third dimension that you can see. And the stars are going around in all sorts of ways. There isn't any one way that the stars are all going around. Unlike the spiral galaxy, where everything is nicely ordered and everything is going around together, more or less. In the elliptical galaxy, it's much more of a free-for-all. They're all going around the centre of the galaxy, but they're not going around in any ordered way. They're going around any which way they feel like, basically. So there is lot less order in an elliptical galaxy. The other thing you can see about them, here's an E5, so this is a bit of a stretched one, is that they are predominantly red. There is almost no blue in an elliptical galaxy. So that also tells us from what we've just learned that there are really no new stars, or very, very few new stars being formed in elliptical galaxies. So we often call these red and dead objects. They're sort of retirement homes for stars. There is no more gas, or no gas that is easily usable within the galaxy to make new stars from. So they've sort of shut down and finished. This is a very spherical version. This is an E0 M89. Here's a Hubble picture of that. And here's an E7. So this is about as stretched as you can get in the elliptical. Theoretically, you could have an E8, E9, E10, etc., because they are just measurements of how elliptical it is. But above E7, there isn't enough sort of structuralness to the galaxy to keep it together. So once you get closer to an E8, it begins to sort of fragment. And this is probably only an E7 because of this this galaxy over here that's sort of dragging it out somewhat. Now, going back right to almost the beginning, I talked about S0s or lenticular galaxies, and they are much easier to describe now. I've talked about the other two. So here is a lenticular, and the simplest way to think of these is they are spiral galaxies, but you can't see any spirals in them. So they have the two fried eggs back to back, or the CD, or whatever you want to call it, but you can't see any spiral arms in them. And you can also see from this image that they are very red in colour. So these are kind of spiral galaxies that have grown old and switched off their star production. So they're no longer making new stars, so that's why we don't see any blue in them. And the blue stars really sort of pick out the spiral arms. And because we're not seeing any blue stars, we can't see the spiral arms either. So that's really why I sort of left S0s or lenticular galaxy, lenticular from, I think, the Latin or Greek, I'm not sure which, meaning lens, so lens-shaped galaxies. So they're much easier to understand once you understand what a spiral galaxy is. They're sort of the remains of a spiral galaxy after it's finished making stars. Then we also come on to the other type he had, the irregular galaxy, here M82. This is normally how you see M82 in the visible. This has ultraviolet and infrared overlays, I think, on this one. So the main galaxy is sort of this part here. It's also called the Cigar Galaxy. And this stuff here is sort of some sort of train wreck that's going on with this. So that's what's making it irregular. Something has either collided with it or something has stirred it up, and we've got this big explosion of stuff which has sort of destroyed the main structure of it. And this one is also called a starburst. So this one is making lots and lots of new stars. I said the Milky Way is making maybe 1 or 2 new stars a year. This is making 500, 300, that sort of order, making lots and lots of new stars. Galaxies often go through this period after something major has happened to them. Everything is stirred up, you get all this gas floating around, the raw material of the stars, and suddenly it finds these new reserves of gas and it can go about in a frantic burst of making new stars. But often it's kind of the final bit. It uses up all that gas making these new stars, and then if we come back in about a gigayear, this will have settled down to something probably red and dead by then. The other type of irregular you get quite a lot of is dwarf irregulars. So these are dwarf galaxies, often hanging around bigger galaxies, and because they are lurking around those bigger galaxies, they often get sort of wrecked a bit by the gravity of the bigger galaxy, so they never get a chance to sort of form a nice coherent galaxy, so they just sort of float around doing whatever they can, often getting smashed into by the bigger galaxy. So they do what they can. So we thought we got galaxies nailed down. Well, we pretty much have. We still use this category from now. Those are the 4 main categories. You will pretty much see every galaxy categorized into one of those, sometimes with subcategories. And it's one of those I want to investigate next, which is the subcategory of active galaxies. But this one spreads across several types, so you can certainly get active galaxies from elliptical and spiral galaxies in some cases. So this came from some work done in the 1940s by American astronomer Carl Seifert. So he was looking at galaxies, and this is one of those he looked at, M106, and it now bears his name as a type, so it's a Seifert galaxy. And one of the things astronomers do to keep themselves occupied with galaxies is to look at how the light changes. So if you were to draw a graph of this like this, so this is sort of distance from the center along here, and this is the amount of light up here, call that L, it sort of goes something like this. So the amount of light, if you just measure going out from the middle to the edge, you can see the light drops off, something like that. It's some sort of an exponential curve that drops away. I'm sure you're all very familiar with exponential curves after COVID. But when he was measuring this in some of the galaxies, he found that this bit of the curve was extremely high. It was much higher up than he measured for most of the other galaxies. So it had a very, very bright center. And after a bit of looking around, he found a few more like this, and he published a paper on it, and that's how they came to be called Seifert galaxies. And after a while, people looked around and found more, and they found another type of galaxy that looked a bit like these, but not quite. They had subtle differences. So we came up with two types of these. So there's a Seifert type 1 and a Seifert type 2. So that was already a bit of confusion. Then as we got better telescopes and new equipment, we started looking at these. And here's Hercules A. This is a galaxy in Hercules. And this is also one of these with a very bright center. But if you can look in other wavelengths, sometimes you get clues as to what's happening. And in this case, if you're looking in the radio spectrum, you can look at what's happening with the gas around the galaxy. And when they looked at that, and you overlay the radio picture over the optical picture, you can see this this very bright part in the center of the galaxy is clearly doing something quite strange, or certainly something very active. It is kicking out stuff from the galaxy, and it's quite difficult to say just how powerful this thing must be to kick out all this gas from the galaxy. I mean, you've got billions and billions of stars in here, each of at least the weight of the sun, all with their gravity, all trying to pull everything back in. So to exceed the escape velocity of the galaxy is quite hard work, but this thing seems to have been doing it for quite a while. So if you remember back to early on, I said if you sort of work out the distance across here, it's about 100,000 light years. And in fact, this is an elliptical galaxy, so it's probably something slightly bigger than that. So 100,000 years at least for light to travel from sort of A to B. Ooh, I can't draw with a mouse. Okay, A to squiggle. So to go from that distance is 100,000 years at least if you could travel at the speed of light. But this stuff out here, you know, by the time you get out here, it's a long, long way away. So it must have been shooting out of that galaxy for millions and millions of years to get that far and to be building up. So this is clearly, this is one of these things we call an active galaxy. It is clearly active. It is doing something quite strange. Here's another one. This one we're seeing from a sort of different angle, Radio Galaxy Centaurus A. Again, you can see this stuff being shot out, and you can see actually shock fronts out here that as the gas being expelled from the galaxy runs into the intergalactic medium, which is almost like a vacuum, but this stuff is coming out quite fast, so you still get the shocks occurring. So there was definitely this subgroup of galaxies called active galaxies that had something crazy going on in the center of them. When we looked even further, we found another group of things, and these are called quasars, for quasi-stellar radio sources. So they were often picked up in the radio initially, but they look very point-like. So they look like stars. That's why they're quasi-stellar. They look like stars because they look like single points rather than fuzzy images. And there's a whole story to be told about how they were found. But eventually, when we did make progress on working out what they were, they turned out to be galaxies a long way away, but very, very bright. And here over this one, you can see a Hubble picture where they've sort of masked out this very bright bit, and you can see the fuzzy galaxy behind it. So these again are active galaxies shooting stuff out. And this is another one. This is a blazar, an even brighter one. So by this point, you're getting actually quite a lot of these strange different types of active galaxies. So we've got quasars, we've got Seyferts, we've got blazars. There are other things called QSOs. There's very radio loud galaxies, radio quiet galaxies. And there's broad line radio galaxies and narrow line radio galaxies. There's a whole profusion of them. I remember when I first had to learn about these, going through them and thinking, oh, no, not another one. Is this going to come up on the exam? All this big confusion of them. But luckily, we made some progress on this, or at least some people did back in the 1990s. And they all have really the same common thing, that they are all driven by a supermassive black hole right at the center of the galaxy. So this is something that is powerful enough to trigger this explosive force. So it's a big black hole, and every galaxy we've looked at in enough detail, it's quite hard to see the very center of a galaxy in sufficient detail, but everyone we've looked at has one of these supermassive black holes. And a regular black hole, a stellar black hole, the remains of a supernova is sort of 10 to 50 solar masses, but these are 1 million to 1 billion solar masses, so they are huge. One of the secrets of astronomy is nobody knows how you make one of these, or at least not yet. But given it is one of those, this actually simplifies everything hugely, because they are all just aspects of the same thing. So this is the sort of cartoon view. So you have the black hole in the center here, this black hole bit here. And anything that goes into the black hole is lost. So that isn't responsible for anything in the black hole itself. But stuff that is falling in, again, it's a bit like a bath plug. It comes spiraling into the black hole, goes round and round, getting faster and faster, hotter and hotter. And this is what generates the radiation. So it's not stuff falling into the black hole, it's stuff that's almost ready to fall in that creates this. And sometimes we get these jets that come shooting out at very high speeds, almost the speed of light, emitting huge amounts of material. And this same picture lets us explain all sorts. So this would be a quasar. If you're looking from this angle, you would see a quasar, because you can see sort of almost looking not quite down the jet, but you can see this very bright object. This would be a blazar when you're looking straight down the jet of it. And here's some of the other broad line and narrow line regions ones. And here's a Seyfert type 1, Seyfert type 2, and they're all just geometric versions. So there's really only two types of those that have the jets. So the jets last for a certain number of millions of years, probably until they shut off. And then you get the picture below the line, and you get all sorts of different forms of those. Sometimes you can see into the black hole almost. That's the Seyfert type 1. You can sort of see through all this material. And Seyfert type 2 you can't. You can't see in there. It's obscured. So that's active galaxies sorted out. What else have we got? We've got collisions. So galaxies aren't particularly static. They all collide over time usually. Most galaxies endure a collision. The Milky Way has certainly had its fair share of them, but mostly dwarf galaxies. So a spiral galaxy can withstand quite a few dwarf galaxies hitting it and survive through it. It's difficult to see these in action because I said it takes 1 billion years or so for anything interesting to happen. So come back in 1 billion years and this picture will have evolved somewhat. But if we look around the night sky, we can see them in different acts. So this one's a much further along in the process of colliding. Then there are a whole load of oddities that I just thought I'd throw in because they're kind of interesting. So the biggest galaxy is not this one. This is just a spiral galaxy for size. If I shrink that down to this, here's the biggest galaxy with the catchy name of IC 1101. And it's a elliptical galaxy, as I'm all sure you all know by now. So elliptical galaxies tend to be much bigger than spiral galaxies on the whole. This one's a sort of Darth Vader galaxy spotted by a colleague of mine looking through some data pictures. You can sort of see Darth Vader's spacecraft in the center here. And to go along with that, we have the Lightsaber galaxy, which is looks like a lightsaber. Unfortunately, this is an infrared picture. It doesn't look quite like this in regular light. This is the furthest galaxy we've seen out of redshift of 11, or 13.4 billion light years away. So this is the furthest galaxy we've yet seen. And here we have a ring galaxy. This is a galaxy without its center. Probably this galaxy here has something to do with that, having done something to it. Another type of galaxy we sometimes talk about is the BCG, the brightest cluster galaxy. Lots of galaxies form in clusters, in groups of either 30 to 50 to 100, even thousands, and they are all orbiting around each other. Unlike us, we're in a very lightly populated area of the universe. There's only 2 major galaxies in our area, but quite a lot of them live in big sort of conurbations, big cities of galaxies. And the big central one is often called the brightest cluster galaxy. So sometimes you hear the BCG. Now, another term that I absolutely love is lurgs, U-lurgs and E-lurgs. I really challenge you to try and squeeze this into a conversation if you have one over the next week or two. But you've been looking at lurgs recently. So lurgs are, you can have a go at guessing what it is, but I'll save you. It's luminous infrared galaxies. So these are galaxies that look fairly uninteresting in visible light, but are extremely bright in infrared. So being the unadventurous people we are as astronomers, we call them luminous infrared galaxies, and that name has stuck. So here's a lurg sitting there doing its lurg stuff. Then we found a whole category of them that were much, much brighter than lurgs. So we thought we'd better have another grouping for this, doing some stamp collecting. So these are ultra-luminous infrared galaxies. So there we go with an ultra-luminous infrared galaxy, or a U-lurg. And then naturally we found an even brighter one, or group of brighter ones. And here we have E-lurgs for extremely luminous infrared galaxies. And as far as I know, that's the limit. We haven't gone beyond that because we're kind of running out of adjectives at that point. And these are all galaxies that have, they're regular galaxies, much like any other galaxy, but they have a high proportion of dust within them. So this dusty, sooty stuff that you saw earlier on in the Sombrero galaxy is a large component of these galaxies. And that stuff tends to soak up the starlight. So it's like a sort of sooty blanket. The light doesn't get through it very easily and gets caught up in this sort of soot that's floating around in the galaxy and doesn't get out of the galaxy typically very well. But all that energy has to go somewhere, so it goes into warming up the dust. And the warm dust starts to glow with heat, which is infrared radiation. So that's why they glow very brightly in infrared. So there we go. Try and squeeze in a lurg into your next conversation. I thought I'd perhaps finish with something that speeds up the development of galaxies, which is simulations. And this is the area that I got into and what I do. So I don't look through telescopes at all. This is what quite a lot of my colleagues at Nottingham do. They go to big telescopes, although increasingly these are run by staff and you don't actually get to go to them and do very much. But this is the ELT, and people are queuing up to go to that when it's finished. Others of my colleagues sit there and do this sort of thing all day. They go through the mathematical framework and they try and come up with equations that govern things, and they can make mathematical models of stuff. I don't get on too well with that because I'm not clever enough really to do that sort of thing. And just an example, we have a group in our department called the Particle Theory Group that work on cosmology and things like this. And this is one of their typical lectures that they hold each week to keep them up to date on their field. That they invite us to attend, and sometimes I do go to some of these lectures, but I didn't go to this one because to me it's just gobbledygook. I cannot understand practically any of the words apart from the and at and which. So if any of you find this quite fluent and would like to just discuss it in the Zoom meeting afterwards, then and please do feel free, but don't drag me into it because I have no idea what it's saying. So I don't do either of those. Instead I use big computers, and this is the big computer. In fact, it's the previous big computer at Nottingham where you can run these large simulations on. And that's what we do. We run big simulations of stars, groups of stars that are forming galaxies, or more typically forming universes. And this all just works with a straightforward equations given by Newton. You can see there it's not a particularly hard equation to solve. You've just got to solve it between millions of different particles. But we cheat a lot of the time because this is what the universe is made up of. So most of it's made up of dark energy, which we absolutely have no idea what it is, but it makes up a lot of it. We also don't know what dark matter is, but we've got a much better idea how it works. Even though we don't know what it is, we sort of know how it's laid out across the universe. And this is much more common than regular matter, which you can see there. Dark matter is 27%, regular matter is around 5%. So if you just simulate things with dark matter, which is much easier to simulate with, you get a good big picture. And we've done that, and we're pretty good at it. So this is a real picture, but drawn by painting dots for every galaxy we can see in the night sky, looking above and below the Milky Way. And you might think that galaxies are just scattered all over the place randomly, but they're not. They're scattered around in groups. This is the sort of thing we try and reproduce in our simulations. And I don't know how well this is going to come out, but this is a simulation that I ran on the Nottingham computer, starting soon after the Big Bang. You can see the time ticking away there in gigayears, and you eventually you can see it sort of condensing down into these structures. This is just dark matter we're looking at here. That's one of the nice things about working with computers. You can see the dark matter because you can colour it any colour you like. It's not subject to the laws of physics inside the computer in the same way. So you can see there it's sort of evolving. I won't run it all the way through, but this is a snapshot from it. And here we can see what it's ended up with. And we can see here some big clumps of galaxies. So here is a huge clump of galaxies. There's maybe hundreds of galaxies in this cluster, all orbiting around each other. There'll be a BCG in the center of that, and lots of small galaxies going around it, all interacting. If we were to look for ourselves, we'd be somewhere out here in the backwaters where there's only just 2 galaxies lurking around, not doing very much. But as I say, our simulations are really quite good on the very large scale. So this is 2 images. The stuff in blue is real data, taken maps of galaxies done by surveys, and the stuff in red is simulated data. And you can see it's obviously not identical, but you can see very similar features in all of them. We get the layout of the universe very good. We don't do so well when we get to the finer detail of the universe in our simulations, but that's stuff we're still working on. Another thing you can do is look at what happens when galaxies evolve and merge. And this is a nice simulation. I hope it's coming out okay over YouTube. This is done by Volker Springel of 2 spiral galaxies colliding. And what you're looking at here is the gas within those galaxies. He's removed all the stars from this. So you're just looking at the galaxy gas and what happens to it when they collide. And the colour is the temperature of the gas. So the blue gas is cold and the red gas is hot. You can see there they've collided, and there's all sorts of stuff happened there. There will be a big burst of star formation at that point. And you can see the gas is really heating up and getting very hot. And now we're getting perhaps supernovas bursting off, exploding stars. And you can see the gas is being blown out of the galaxy at high speed there. Also, the central black holes will have merged together perhaps at some point, and they will produce one of these like quasar effects, which will also shoot out gas. And I said early on that gas is kind of the lifeblood of the galaxy. It's the gas that the galaxy uses to convert and make new stars. And you can see after this, 2 galaxies have finished merging, there is very little gas left over. And what gas there is very hot. Now you need very cold gas to form stars, which is slightly odd, but that's the case. You need it to kind of settle down into a nice cold patch to form stars. So that gives us some insight into that. And one other insight is done from this is quite an old simulation now by NASA of our own local group. So I said there's only really two major groups, galaxies in our local group. There's quite a few dwarf galaxies. So this is what our local group looks like, the Milky Way, Andromeda, and then there's a dwarf galaxy, the Triangulum, M33. And you probably know that Andromeda is on a collision course with the Milky Way, and at about 4 gigayears, we actually get the first collision of the two. You can see there, it doesn't end well for either galaxy. Almost no stars will be hurt in this, but some of them will get thrown out of the galaxy and disturbed. And these two galaxies are now in deadly embrace, and they finally settle down and make something. And you can see what started off there as two really nice, beautiful spiral galaxies has now ended up in a train wreck. And what we have there is an elliptical galaxy, most probably called Milkdromeda or something like that. So a date for your diaries, 4 billion years in the future. Go on holiday if lockdown is finished by then, because it's also the time that our sun sort of begins to run out of fuel and swells up and consumes the Earth. So it's a pretty bad year all around that time. So time to be somewhere else. Just finish up very quickly with some open questions, things we don't understand. This is a picture of a black hole that was on the news last year, very famously. But that's one of the open questions in galaxies. They all seem to have this giant supermassive black hole at the center of the galaxy. We really struggle to see how you make one of those in the time available, because we can look right back into almost the beginnings of galaxies, and some of those have these giant supermassive black holes. So they're not something that's happened over 13.8 billion years, the age of the universe. They can happen relatively quickly. So we're still at a loss to have a good explanation for that. Another subject that we're working on quite a lot at Nottingham is when you look at how you could change some of these blue spiral galaxies into these red elliptical galaxies. There are two things that happen. One is they change in color, so they go from blue to red. And the other thing is they change in mass, so they get bigger. And there's two possible ways they could do that. They could get redder and then get bigger, or they could get bigger and then get redder. We don't really know which way they go. And there is this bit between them which we nickname the Green Valley, where very few galaxies are found. So that's one thing that we're trying to do, and Nottingham is trying to understand how these galaxies change from one type to another. And what are we going to use to explore this? Well, coming up, there's some very nice tools. The Gaia mission, which is mapping our Milky Way, gives us our best accurate star map for the Milky Way. It's kind of like making a GPS for the Milky Way, and lets us do several things like this. This is some of the Gaia data processed by ESA, where they just looked at all the stars and how they are moving and picked out some stars that are moving extremely rapidly. These ones outlined in yellow. They're moving far too fast to actually stay within the galaxy. So these are either stars that have dropped in from the galaxy from elsewhere and are just passing through, or quite possibly they've been given a bit of a kick by a sort of an almost nearby close collision with another star, and they've been shot out of the galaxy now. Here's another tool that we're going to use. This is the James Webb Space Telescope. If you may have seen the news that this has just been delayed due to the COVID crisis. It was due to be launched. Well, it's been due to be launched for many years, but it was due to be launched about March 2021, but that looks like it's going to slip again. Part of the problem with this, which is way behind schedule and way over budget, it was envisaged in 1990, well, somewhere in the mid-1990s, soon after Hubble was launched, to be launched in about 2006 at the cost of somewhere around $500 million. So it's still not been launched. Here we are in 2020, and still going to be at least a year and a half yet. and is now cost about $8.5 billion, which is a lot of money, and it's sucked a lot of money out of a lot of other things that NASA could have been doing. So lots of people are going to be grateful in lots of ways when this is launched, and finally not so much of a drain on NASA's budget. But part of the problem with this is it's quite a big telescope. I think it's 6-meter mirror, so it's going to be the biggest telescope mirror in space. But the problem is you can't fit something that size into a rocket cone. It has to be about this size to fit into a rocket cone. So once it's launched, you have to do the unfolding, which is somewhat like highly technical origami or something, or reverse origami. And all this has to be done automatically and work perfectly a long way from the Earth. So this is going to be parked about 1.5 million kilometers away from the Earth, way beyond the moon. So you won't be able to go and do any servicing missions for this. And there are about 300 separate processes it has to do to become a functioning telescope. And any one of those could potentially go wrong. So that's why they're spending so long checking it out. So that will be a great new telescope. People are chomping at the bit to use it. So fingers crossed nothing bad happens to it. The next big thing in radio telescopes is this thing, the Square Kilometre Array, a big array of telescopes scattered all over South Africa and Western Australia that has incredible resolution for radio astronomy. And the next biggest thing in optical telescopes on the ground is going to be this one here, the ELT over here, the extremely large telescope next to the VLTs. These are sort of some of the biggest telescopes on the Earth at the moment with 8-meter mirrors. The ELT, so 8 meters is bigger than most rooms, but the ELT is a just less than 40-meter mirror. So this is getting on for half a football pitch in size, an enormous mirror, and this is going to be an enormous structure. So you can see how big it is compared to the VLTs over here and the Arc de Triomphe, for instance. So it's not going to be far short of the size of a football stadium when it's finished. It's just a few other pictures. It used to be called the EELT for the European Extremely Large Telescope, because it's a European consortium that are putting it together, but I think they're back to the ELT now. And 2026 is probably the first light time for that. If you want to see what a 40-meter mirror looks like, here it is laid out in cardboard, so you can see just how big this monster will be. So that's my final slide, more or less. Just a quick wrap up. So the summary is galaxies are really big. So 400 billion stars in a galaxy, and I didn't say, but there's about 2 trillion galaxies in the universe that we know of, roughly. So lots and lots of room for expansion, lots of room for everybody. Research continues, and some of the questions out there, and new telescopes will help a lot be able to see further and further back, and also in more detail. So thank you very much for listening. Assuming there are some people listening, I can see on the stats over there are perhaps some people listening. So I'm going to kick off a Zoom talk. I'm going to just post the link hopefully in the chat there, so that anybody who hasn't seen it can pick it up from there. But I'll be starting that in a couple of minutes. So please come over there. Feel free to either ask questions about the talk, ask questions about astronomy, have a social chat, show what sorts of cake you brought along, what sort of drinks you're drinking, anything like that. Anything goes. So thank you very much for listening, and I hope you found at least some of that interesting, and it's been informative. So I'll stop things there, and we'll swap over to the Zoom meeting very, very shortly.